Hello everyone, welcome back to day 5. So far, we have explored artificial intelligence, machine learning, deep learning, and generative AI. Today, we're taking the next step and looking at one of the most exciting applications of deep learning, large language models, or LLMs. These are the technologies behind AI tools like ChatGPT, Claude, Gemini, and many other assistants you use today. By the end of this session, you will understand what an LLM is, why it feels so intelligent, how it generates responses, its limitations, and some important AI concepts that everyone should know. Before we understand LLMs, we first need to understand NLP, which stands for Natural Language Processing. Humans communicate using natural language, English, French, Arabic, and many others. For computers, understanding these languages is much more difficult than processing numbers or simple commands. NLP is the field of AI that helps computers understand, interpret, and generate human language. You already interact with NLP every day. When you use Google Translate, ask a virtual assistant questions, receive a spam email warning, or chat with chatbot, you are using NLP technologies. Over the years, NLP has improved dramatically, and one of its greatest advancements is the development of large language models, or LLMs, which we'll explore next. Now that we know what NLP is, let's answer the big question. What exactly is a large language model? Now let's break down what large language model actually means. First, large doesn't just mean the model is big in size. It means it has been trained on an enormous amount of text and contains billions of learned parameters, allowing it to recognize complex language patterns. Next, language means its primary job is to understand and generate human language, whether that's answering questions, writing emails, translating text, or explaining difficult concepts. Finally, model simply refers to a trained AI system that has learned patterns from data. Instead of memorizing every sentence, it learns relationships and structures within language. Together, an LLM is an AI system trained on massive amounts of text that can generate human-like responses. A common confusion is thinking NLP and LLM are the same thing. They are related, but they are not identical. NLP is the bigger field. It's the area of AI that focuses on making computers understand and work with the human language. An LLM is a specific type of AI model inside this field. It's one of the most advanced approaches used today to solve NLP problems. So, NLP is the whole category, while LLM is one powerful technology used within that category. Training an LLM isn't about storing answers. It's about learning patterns from an enormous amount of text. First, developers collect a huge dataset containing books, articles, websites, and many other publicly available text sources. Before training, the data is cleaned by removing duplicates, low quality, or irrelevant content. The text is then converted into tokens, which are the pieces of text the model works with. During training, the model is shown part of a sentence and asked to predict the next token. At first, its predictions are mostly incorrect. After each prediction, it compares its answer with the correct one and adjusts its internal parameters to improve. This process is repeated billions of times across billions of examples. Over time, the model becomes better at recognizing grammar, context, facts, writing styles, and relationships between words. By the end of training, the model hasn't memorized every sentence. It has learned statistical patterns in language that allow it to generate coherent and contextually relevant responses. For example, the training sentence is, The Eiffel Tower is located in. Model predicts London. The correct answer is Paris. The model updates its parameters. After seeing millions of similar examples, it becomes much more likely to predict Paris correctly in the future. Earlier, we learned that an LLM improves by making predictions and correcting its mistakes. But what exactly changes each time it learns? The answer is its parameters. Think of parameters as the model's internal settings or learned knowledge. They are numerical values that are adjusted during training. Each adjustment helps the model become better at recognizing patterns in language. For example, after seeing millions of sentences, the model learns that words like doctor and hospital often appear together. Modern LLMs contain billions of these parameters. They don't store sentences like a database. Instead, together they represent what the model has learned about language. It's also important to remember that having more parameters doesn't automatically make a model better. The quality of the training data, the training process, and the model's design all play major roles. So, more parameters do not always mean a better model. Data quality and training also matter. Now we know what an LLM learns, but how does it decide which words in a sentence are the most important? That's where one of the biggest breakthroughs in AI comes in. Attention. One of the biggest breakthroughs in AI was the introduction of the attention mechanism. Earlier language models struggled with long sentences because they often lost track of important information. Attention solved this problem by allowing the model to focus on the most relevant parts of the text. Think about how humans read. When you see the word it in a sentence, you look back to figure out what it refers to. You don't give every previous word the same importance, you focus on the ones that make sense. LLMs do something similar. They don't treat every word equally. Instead, they assign more importance or attention to the words that help them understand the sentence correctly. This ability to focus on relevant information is one of the main reasons modern LLMs generate much more accurate and natural responses than older language models. For example, the sentence is, "The cat chased the mouse because it was hungry." The question is, who does it refer to? The cat. Using attention, the model focused on the relevant words to understand that it most likely refers to the cat, not the mouse. Let's look at what happens inside an LLM. Imagine the model is reading a sentence one word at a time. Instead of only looking at the previous words, every word is allowed to look at all the other words in the sentence. For each pair of words, the model asks, how important is this word for understanding my current word? It then calculates an attention score for every word. Words that are more relevant receive higher scores, while less important words receive lower scores. The model combines this information to build a richer understanding of the sentence before predicting the next token. This process happens for every word in the sentence simultaneously. That's why modern LLMs understand context much better than older language models. A fun analogy. Imagine you are reading a mystery novel. When you read "he was arrested," your brain immediately asks, who is he? You quickly scan previous pages, but you don't reread every sentence equally. You focus on the most relevant clues. An LLM does something similar. It scores previous words, focuses on the most relevant ones, and uses that information to understand the current word. Attention allows every word in a sentence to communicate with every other word before the model decides what to say next. Another example, the trophy doesn't fit in the suitcase because it is too big. When processing it, the model checks. For the word trophy, the importance is 5, suitcase 3, fit 2, because 1 and the 1. The model gives the highest attention to trophy, helping it understand what it refers to. How does LLM generate a response? Many people think chatbots writes an entire paragraph in one step, but that's not how it works. It generates text one token at a time. After you type a prompt, the model analyzes the context using its learned parameters and attention mechanism. It predicts the most likely next token, adds it to the response, then repeats the process. Each next token becomes part of the context for predicting the next one. The cycle continues extremely quickly until the response is complete. Although it feels like the model is thinking ahead, it's actually making thousands of tiny prediction decisions one after another. For example, the prompt is artificial intelligence is 3 dots. The model might generate artificial intelligence. Artificial intelligence is A. Artificial intelligence is a branch. Artificial intelligence is a branch of. Artificial intelligence is a branch of computer. Artificial intelligence is a branch of computer science. If LLMs are so good at generating text, why do they sometimes give incorrect answers or invent facts? Let's explore one of their biggest limitations: hallucinations. One of the biggest misconceptions about LLMs that they always correct answer is that they always know the correct answer. In reality, an LLM is designed to generate the most likely sequence of tokens based on its training. It doesn't stop to check whether a fact is true unless it's connected to external tools or reliable sources. Sometimes, when the model doesn't have enough information or when the question itself is misleading, it may generate an answer that sounds completely believable but is actually incorrect. This is called a hallucination. It's important to remember that hallucinations aren't intentional. The model isn't trying to deceive you. It's doing exactly what it was trained to do: predict the next token. That's why AI should be used as an assistant, not as the final authority on critical decisions. Early AI systems were usually designed for one type of data. Some models only process text, while others specialize in image or speech. Modern AI is becoming multimodal, meaning it can work with several types of information at the same time. Imagine asking an AI to analyze an X-ray image while also explaining the result in simple language, or uploading a chart and asking it to summarize the trends. That's the power of multimodal AI. This makes AI far more useful because in the real world, we rarely rely on just one type of information. We combine what we see, hear, read, and say to understand a situation. And multimodal AI is moving in that direction. Modalities means type of data. Common modalities for text, articles, emails, conversations. Images, photos, diagrams, documents. Audio, speech, music, sounds. Video, videos and animation. Speech, spoken responses and conversations. For example, you upload a picture of a plant and ask, "Why are these leaves turning yellow?" The AI analyzes the image, understands your question, explains the possible causes, suggests solutions. Why is multimodal AI important? It understands the world more like humans, combines information from different sources, creates more natural and useful interactions. Some real-world examples: upload a handwritten note and ask the AI to convert it into typed text. Translate a photo of a restaurant menu into another language. Upload a PDF and ask for a summary. Speak to an AI assistant and receive a spoken response. Generate an image from a text prompt. If AI can understand text, images, audio, and more, what if it could also take actions on your behalf? That's where AI agents come in. So far, we have looked at LLMs, which are excellent at understanding and generating language, but they usually stop after giving you an answer. AI agents go a step further. Instead of only answering questions, they can perform tasks on your behalf. They can break a goal into smaller steps, decide what to do first, use external tools like web browsers or calendars, and continue working until the goal is completed. Think of an LLM as the brain that understands language, while an AI agent is like a digital assistant that uses that brain to take real actions. This shift from answering to doing is one of the biggest trends in modern AI. For example, the goal is book the cheapest flight to Dubai. Traditional AI say you can search on airline websites. However, AI agent searches airline websites, compares prices, finds the best option, books the ticket with your permission, and sends you the confirmation. So key capabilities: reasoning, planning, tool usage, memory, goal-oriented decision-making. Some real-world examples: read emails and draft replies, schedule meetings on your calendar, compare products before purchasing, generate code, test it and fix error, analyze business reports and create summaries. As AI becomes more powerful, safety becomes increasingly important. An AI model doesn't automatically understand the human values or know what information is appropriate to provide. It follows patterns it learned from data. Guardrails are additional safety systems placed around AI to reduce harmful behavior. They can filter unsafe content, protect user privacy, and guide the model toward better responses. They answer, what should the AI not do? For example, don't provide instructions for harmful activities. Don't reveal private user information. Don't generate certain unsafe content. Warn users when information may be unreliable. Think of guardrails like a car's brakes, seat belt, and speed limit. They are concrete safety features. For example, without guardrails, user, how can I harm someone? AI provides dangerous instructions. With guardrails, AI reply with, I can't help with harming someone, but I can discuss safety or conflict resolution. What is AI alignment? AI alignment is the process of making AI systems behave according to human values, goals, and safety expectations. AI alignment is a broader concept. It focuses on making sure AI systems pursue goals that match human intentions and values. The challenge is not only making AI more intelligent, but also making sure that intelligence is used responsibly. The goal: make AI helpful, safe, and aligned with the human intentions. So AI alignment: how do we make AI behave in a way humans actually want? It includes understanding human goals, making AI follow instructions correctly, reducing harmful behavior, making AI helpful and trustworthy. Think of alignment like making sure the car is going to the correct destination. A car can have perfect brakes, but if it's driving to the wrong place, there is still a problem. Easy example with an AI assistant. You ask, help me write an email. The AI understands your goal. Make it professional, keep your meaning, don't change your intention. Guardrails, the AI avoids adding private information, creating harmful content, making false claims. So guardrails are safety rules that control AI behavior. Alignment, ensuring AI goals match human intentions. AI engineering is about creating AI systems, training models, writing algorithms, managing data, and building AI applications. AI literacy is different. It means understanding how AI works, knowing its strengths and limitations, and knowing how to use it effectively. In the future, AI literacy will become a valuable skill across almost every field. A designer, doctor, marketer, developer, or business owner may not build AI models, but they can all use AI to improve their work. The people who benefit most will not necessarily be the ones who know the most complex algorithms, but the ones who know how to combine human skills with AI tools. Today, there isn't just one LLM. Many companies have developed their own models, each with different strengths and design choices. OpenAI developed ChatGPT, Anthropic created Claude, Google built Gemini, Meta released Llama, and DeepSeek introduced its own family of models. While these models may differ in performance, safety approach, multimodal capabilities, and efficiency, they are all based on the same fundamental concept we have discussed throughout this session: learning language patterns from massive datasets to predict and generate text. Choosing the best model depends on the task. Some are stronger at coding, others at long document analysis, reasoning, creativity, or multimodal understanding. Although these models are different, they all share the same core idea. They are large language models trained to understand and generate human language. The differences are mainly in training data, model architecture, optimization techniques, safety, and alignment methods. Let's quickly recap our journey so far. On day 1, we introduced artificial intelligence, explored what it is, the different types of AI, and how AI is already part of our daily lives. On day 2, we focused on machine learning and learned how computers improve by finding patterns in data instead of being explicitly programmed. On day 3, we explored deep learning, where artificial neural networks with multiple layers enable AI to solve more complex problems, such as image recognition and speech processing. Finally, in days 4 and 5, we moved into the world of large language models. We learned how LLMs fit within NLP, how they are trained, how attention helps them understand context, why they sometimes hallucinate, and how modern AI is evolving through multimodal systems, AI agents, and responsible AI practices. Today, you now have a complete picture of how modern conversational AI systems work, from the foundations of AI all the way to the technologies powering tools like ChatGPT. That brings us to the end of today's session. I hope you now have a much clearer understanding of large language models, how they work, their limitation, and where AI is heading in the future.